So, what does a chemical engineer actually do? I mean, the title sounds super complex, right? But their work is literally everywhere, from the gas in your car to the medicine you take. Today, we're going to go inside the mind of an engineer to see exactly how they pull it all off. Just think about it for a second. Almost everything we use and touch started as some kind of raw material. So, what's the secret sauce? What kind of knowledge does it take to transform all that stuff safely and efficiently into the products we need? We're going to find out in a pretty cool way. We're going to take a peek at the final exam for a chemical engineering student. By walking through the questions they have to answer, we'll get a perfect roadmap of what an engineer needs to know to do their job. So, an engineer's day doesn't really start in a lab with bubbling beakers. Nope. It starts with the fundamental principles of chemistry. It all begins with the absolute building blocks of matter. Okay, check out this table. It breaks down the fundamental forces that hold our entire world together. An engineer has to understand everything from those super strong ionic bonds, like in your table salt, to the much weaker van der Waals forces. And you might be asking, why? Well, because if you don't know how atoms are going to stick together, you have no chance of building something new or taking it apart. Their master key for understanding all of this is, of course, the periodic table. Knowing exactly where an element sits on this chart, whether it's a transition metal or a halogen, tells an engineer how it's most likely going to react. And that knowledge is absolutely crucial for any chemical process. All right, with that fundamental knowledge locked in, now our engineer can head into the lab for their first real task. And in this world, let me tell you, precision is everything. You know, preparing a solution isn't just about dumping some powder in water and stirring. It's a meticulous, multi-step process designed to eliminate any and all error. You have to calculate the exact mass, weigh it perfectly, dissolve it carefully, and then dilute it to a precise final volume. So you might be thinking, okay, I get it, be precise. But just how precise are we really talking here? What's the big deal if you're off by just a tiny, tiny bit? Well, to make one very specific saltwater solution for an experiment, you need exactly 2.925 grams of sodium chloride. Not 2.9, not even 2.93. We are talking about accuracy down to the thousandths of a gram. That's essential. And this is where that precision becomes so critical. In a university lab, a small mistake, it might ruin an experiment. It's annoying, but you move on. But in a massive chemical plant, that same tiny mistake could ruin an entire batch of product, costing the company a fortune. Okay, so now our engineer is switching gears, moving from the world of pure chemistry into biology. They're about to start working with things they can't even see with the naked eye. Their main tool for this part of the job is the good old light microscope. And understanding how every single part works, from the eyepiece you look through to the objective lenses that do the real work, is key to what comes next. So, how on earth do you see these tiny life forms? It's a whole process. You have to prepare a smear on a slide, use a little heat to fix it in place so it doesn't wash away, and then, this is the magic trick, you apply a stain. See, most microbes are basically transparent, so the stain is what makes them visible, allowing the engineer to actually see them and even count them. But a chemical engineer doesn't just look at microbes for fun. The real goal is to put these microscopic powerhouses to work for us. The secret weapon here is something called an enzyme. You can think of enzymes as nature's catalysts. They're like tiny biological machines that can perform really complex chemical reactions incredibly fast, all without needing massive amounts of heat or pressure. So what can we do with this amazing power? Well, just about everything. Engineers use fermentation to brew beer, to bake bread, to create biofuels, and even to produce life-saving pharmaceuticals and antibiotics. It's a cornerstone of the entire biochemical industry. So far, we've seen our engineer build solutions and harness life. But now we come to what might be the single most important part of their job, the part where the stakes are the absolute highest: safety. After using all those trillions of microbes, what do you do with them? There are really only two paths. The right path, proper disposal, leads to neutralized waste and a protected environment. The wrong path can have disastrous, and I mean disastrous, consequences. I'm not exaggerating here. Improper disposal can lead to pathogenic contamination, causing disease outbreaks. It can cause huge environmental disruption, like those nasty algal blooms you see that choke all the life out of a lake. It can even lead to the release of dangerous toxins. The stakes are incredibly high. So how does an engineer prevent this nightmare scenario? They create a multi-layered defense system. It starts with pre-treatment to kill off the dangerous microbes. That's followed by primary and secondary treatments to clean the wastewater. And finally, and this is so important, there's constant monitoring to make sure the system is working perfectly 24/7.
This quote just nails it, doesn't it? From the smallest atomic bonds we'll never see to the largest industrial safety systems that protect all of us, an engineer's work truly shapes our world, often in ways we never even notice.
So you see, being a chemical engineer is about so much more than just chemistry. It's about precision, it's about harnessing nature, and maybe most of all, it's about managing huge risks to keep us all safe. It really makes you wonder, doesn't it? What other invisible feats of engineering are out there, quietly protecting you right now?